now I'd like to introduce finalist number 3. She is a graduate student in physics and quantum science at Harvard University, and she works with ultra-thin 2D materials, and she studies their special topological properties. Now, she actually grew up close by. She's from Newton, Massachusetts, and she told us that she remembers coming here to the Museum of Science when she was a kid. So please put your hands together to welcome Rebecca Engelke to the stage.
Electronic devices, like our phones and computers, are getting more powerful, but also getting smaller. As we continue to shrink this technology, we're getting close to the quantum scale, the scale of single electrons. And we can't just make the same type of circuits, but smaller. We're going to need new designs based on different physics. All these devices are made up of electrons flowing through wires of conductive material. In theory, all electrons make it through. But in reality, there are dirt and imperfections in materials that can bounce some electrons out of their path, meaning energy and information is getting lost. If we want to work with single electrons, this becomes a big problem. To study the conduction of a material, we look at its behavior over a range of energies. At the quantum level, even a conductive material has a gap, energies at which it can't conduct. And its conductive energies are called bands. And the science of materials is all about designing or discovering materials that have bands and gaps where we want them. If we want this material to conduct, we could do so by closing the gap like this. But this is not the best way to close a gap, because if we look over here where this piece of dirt is, that can distort the bands and cause the gap to open back up, meaning it can't conduct anymore. There's actually a better way to close a gap, and that involves the concept of topology. Topology is a field of math that describes what shapes can and cannot be smoothly transformed into each other. To say that two things have different topologies means that to turn one into the other, you have to do something drastic, like cut a hole in one of the shapes. For example, suppose I gave you 2 links of a chain, and I come back a day later and find that they're unlinked. I know nothing about what you did all day, but I do know one thing. I know that at some point you did something drastic to one of the loops. You pried it open. Linked loops and unlinked loops have different topologies, and the power of topology is that it allows me to know that this intermediate state happened. Here I have 2 materials with different topologies, which I know because the second material, the positions of the orange and blue bands are swapped. If I try to put these materials into contact, the bands want to smoothly connect, but to do so, they have to do something drastic. They have to pass through each other and close the gap, which means that there's ability to conduct right there. The important thing is that if I look where this piece of dirt is, the dirt causes the bands to become distorted, but they still have to cross, so there's still conduction, even if it's a little off to the right. So an electron will find a conductive path through this material no matter what. To compare, in a normal material, dirt causes the electron to bounce out of its path, but at the junction of 2 topologies, all the electrons can make it through. In my research, I've worked with this material in which the dark and light triangles are 2 different topologies. Topological materials are an exciting way to control electrons down to the smallest scales. Thank you.
Wonderful. Let's hear it for Rebecca Engelke.